So, we have been discussing the MESFET IV characteristics based on a model called Shockley's model. This was the original model given at least 5 decades back, 1950s, but still holds good for most of the structures, unless you have too much reduction in the size. So, what we did, I just projecting the diagram once again, we took we found out what is the relationship between the drain to source voltage and the drain current. Just to go back to what we have drawn, I just draw side by side the characteristics here. You do not need to do that, or I will put it here. Put it there, and in fact, what I will do is I will reduce the size here, so that we can accommodate everything. Semi insulating gallium arsenide. Now, what we do is we have this VDS versus ID characteristics. So, what I want to point out here is initially when the VDS is small compared to VBI minus VGS, it is linear characteristics. It is linear because depletion layer is almost flat there. The drop in this region is small compared to the drop across the depletion layer. We have seen that. Beyond that point, the shape of the depletion layer comes like this, and the shape of the resistor becomes narrower and narrower. Resistance goes up, therefore, the current does not increase linearly. It does not increase linearly, it deviates from linearity. That goes like that. And at a particular point, when this depletion layer pinches off the channel completely, the voltage drop here, that is VD sat. We call it a VD sat because at that point this has almost closed the channel, and there is a small opening left, so that whatever current enters here goes through the thing. So, that is the saturation voltage. In fact, we have seen what this threshold saturation voltage is, and beyond that point current saturates, even though the VDS changes. What we are telling is between these 2 points the voltage does not change, because if it is increasing, this will have to widen. There is no scope for that widen, because then the current will fall. So, this does not change. So, the question is, where has that remaining voltage that you applied gone? That point I did not mention yesterday in the last lecture. That is why I am just taking this up. This extra voltage goes up. Let us take the case where VGS equals 0. This is connected to that, and this has saturated at that point. So, extra voltage, this is 0, that if you increase the voltage beyond this point, it appears across these 2 junctions, Shockley barrier junction and ohmic contact. It is like a diode. So, the reverse bias, this is plus, this is ground. This reverse bias voltage cannot appear across this, because if it appears across that, current would tend to fall, then it will open up. So, that dynamic equilibrium has reached. So, beyond that point, if I increase the voltage, the depletion layer actually will spread like this, leaving that opening still. It is spread like this. I do not have place to show it here, but it will be far enough, other it will punch through into that. So, that is the way the depletion layer spreads up. The voltage beyond this voltage, that is VD sat, the VD sat, VDS saturation, beyond that point that appears across that. So, there is a 2-dimensional effect coming up here. All through it is 1-dimensional effect. In fact, what all you have been talking of, gradual channel approximation, does not hold beyond this point, because that is a 2-dimensional effect. The field will be going in that direction. With that introduction, or supplementing what we have been talking of yesterday or in the previous lecture, we will go ahead further with the discussion. Okay. But the key thing to remember is that this what we are assumed is this point merges with this region, and beyond that point the depletion layer just spreads in the lateral direction, it does not move in the vertical direction. So, that is the current saturation. So, we have also said, just quickly go through in a couple of minutes, the saturation voltage, drain to source voltage plus the voltage across the depletion layer, VBI minus VGS, okay, that is Vp 0. That voltage Vp 0 and that voltage is equal to whatever voltage is present here, which is VBI minus VGS plus that drop, that is Vd sat. That is the Shockley's condition for saturation. Okay. So, with that assumption, we just wrote the equation for I V characteristics using Ohm's law, and we arrived at this. I do not want to go through that again, because we have gone through it in detail. This expression that we get, and look at that Vd sat, we have substituted Vp 0 plus VGS minus Vbi. I substituted from this equation for this here, that is Vp 0 plus VGS minus Vbi, and I have retained other terms as it is. Now, one thing that we have defined at this point is a threshold voltage. It is a very important parameter for the device, that is Vbi minus Vp 0. Okay. So, actually here this is VGS, and I can write this term as VGS minus within bracket Vbi minus VGS, which is actually okay, VGS minus Vtn, threshold voltage. So, what we said is the threshold voltage is the voltage that you must apply to the gate, so that the channel just pinches off at the source end. Without any drain voltage, if you apply voltage to the gate, that depletion layer should all through move. That is actually threshold voltage. That is we found out or defined yesterday, it is equal to Vbi minus Vp 0. Okay. So, all that we do is substitute for that Vbi minus Vp 0 threshold voltage, all that we do, and then pull out this Vp 0 out of that, make an approximation that VGS minus Vtn is small compared to Vp 0. Okay. Using that relationship, you get that. So, after deriving the expression for the current, we said the current saturates when there is pinch off at the channel drain end, and then we have defined the term threshold voltage, Vbi minus Vp 0 as threshold voltage, substituted in that equation, and made an approximation that VGS minus Vtn, that is VGS dash, is small compared to Vp 0. We get this, that we rewrite as pulling out these two terms, this one, substitute for G naught and Vp 0, all that put together, and cancelling out. G naught is channel conductance, okay, and Vp 0 is Q and D is A square by twice epsilon r epsilon 0, and cancelling out Q and D into A, Q and D into A, you get that term. In fact, we have done that in the previous lecture. So, you get this actually is equal to, this is where we stopped last time, mu n CSW by 2L VGS minus V threshold voltage square. It is exactly same as that of the MOSFET equation. All the difference is the particular term, capacitance. These are all capacitance per unit area. Okay. And here, if you take a look at this, mu n, if I am talking of all silicon, mu n will be same as that of silicon, but there will be one difference. This device, the mu n is governed by bulk mobility, the mobility in the bulk region. In the MOSFET, the mobility is governed by mobility at the surface, because we invert that in the inversion. This is not a device which works on inversion layer, it is a device which works on bulk conduction. So, bulk mobility plays a role here. bulk mobility is higher than the surface mobility. If you take silicon, 1500 centimeter square per volt second is the mobility of electrons in the bulk. In the surface, due to scattering in the surface, what is the mobility? About 1000. People even worry about getting 1000. If you get 1000, your joy is quite high. You are very happy, because that is what you get. If a surface is rough, you will get 900, 800 of that order. Okay? So, it is not a device whose mobility depends on surface mobility, it is a device whose mobility depends on bulk mobility. So, even if you think of silicon device itself, MESFET, that would be better. But unfortunately, the barrier heights are small in the case of silicon 5bn, because band gap is 1.1. If you take 2/3 of that, about 0.7, 0.75. That is why they are, and also your A star etcetera are large. So, J naught is large in those cases. So, you not really talk of MESFET in the case of silicon diodes, but you can talk of JFET in the case of silicon diode. That will be same. The same equation holds good in the case of JFET, absolutely no problem. What is the difference? That Shockley is replaced by a P plus junction. Instead of metal semiconductor, it will be P plus N junction. All the theory, please understand that all the theory that we have been talking of here, all the equation that we have derived for MESFET are exactly same as that of JFET. We have not talked anything different. Only thing that we made difference is there is an insulating layer below and there is active layer here. You can have a P plus diode on the top, P plus N junction on top, you can have from bottom also. Then you can have depletion layer coming from both ends. So, instead of talking of A here, you may have 2A there, or you can talk of A by 2 and total thing as A, both same thing. Okay. So, what we are saying is the mobility that we are talking of here is better, and when you switch over to gallium arsenide, you can actually make better MESFET compared to a MESFET in silicon. So, in the case of gallium arsenide, the mobility of electrons is 8500 ideally. If not 8500, you will at least get 5000 centimeter square per volt second. So, 3 to 4 times higher mobility. And CS, what is CS? Okay, you just see here the C oxide is epsilon oxide into epsilon 0 divided by T oxide in the MOSFET. T oxide is oxide thickness, permittivity of silicon dioxide, epsilon 0 8.854 into 10 to the power minus 14 farads per centimeter. I am not multiplying by area because per centimeter square this is. CS, what is CS? You just take a look at here, that is the capacitance of the depletion layer itself, epsilon r epsilon 0 into A divided by A. So, that is the capacitance of the channel if the channel is fully depleted per unit area. Capacitance of the channel per unit area if the channel is fully depleted totally uniformly, that is the capacitance. Okay. Now, notice here between these two, for silicon this is close to 4, people talk of 3.94 in that range, 4, and this is for gallium arsenide 12.8, silicon it is 12. So, whether you talk of silicon MESFET or JFET or silicon MOSFET, this term is larger than that, at least about 4 times larger. Plus you have got the mobility term. So, all put together you will see that you will see here that this particular term altogether is larger, maybe at least by a factor of 10 or more compared to silicon MOSFET. So, this tells you that you will get IDS larger than for a given voltage swing VGS, the voltage VGS with threshold would be representing the voltage swing. For a given voltage swing, you will have a larger change in the current, which would mean that you get a better transconductance for a given size, for a given W by L ratio, because this is larger than that of C oxide, that is CS, and because mu n is larger in gallium arsenide, and also because of the bulk properties, it is larger than that of mu n in silicon, you get this factor much larger. You will get it about 10 to 15 times larger, because mu n is larger, CS is also is larger. So, this is one of the better things that has happened. The moment gem is larger, what is the implication of that? The driving capability of the device is better. If the drive, that is delta ID by delta VGS. For a given change in voltage, the current change is larger. So, driving capability is better for a given size. When the driving capability is better, what is the implication of that? It can charge capacitors fast. Okay? It can charge the capacitors fast, because more current can be pumped in at a short time. What does it mean? It implies you are looking into a device which can make the circuit performance faster. So, that is where gallium arsenide based devices are better performers. They perform better and better with higher speeds than compared to silicon based devices and also MOS based devices. Okay. In fact, I was just mentioning some other day some people in some of the companies in US who were coming here for just in a discussion. You are thinking of the MOSFET with thinner and thinner and thinner oxides. You remove the oxide, you get MESFET. That should give you better performance, because you talk of bulk mobility. It is easily said than done. There will be a lot of problems associated with that, but I am sure people are moving in that direction. Finally, remove the oxide. You do not have to worry about all those things. Okay? In fact, you can see the flavor of that when you discuss the gallium arsenide MESFET properties. One of the things is this: better transconductance, better speed. Now, in this context, I want you not to lose track of what we discuss usually in JFET, particularly in books like in the undergraduate books like the Millman and Halkias. You know that you see a different type of form. You do not see the term threshold voltage. Okay? But let us see whether it is different from that equation that we have derived. Under what conditions it becomes that equation. The equation that you see, will see. The equation that we had just now was, just let me go back to that once to make sure that what we are doing is right. Okay? This is the equation that we wrote. That we simplified and put it as mu n CSW by 2L VGS minus P threshold whole square. So, same equation G naught by 4 Vp 0 into G naught by 4 Vp 0 into VGS minus VTN V threshold square. I am substituting back for V threshold VBI minus Vp 0. In fact, I am going back to the equation which we have written in a different form before that final simplification. So, here if I remove this VBI, when can I remove the VBI? I can remove that if that is small compared to that. If I am talking of VBI of about 0.6, 0.7 volts or 0.8 volts, and if I am talking of Vp 0, 3 to 4 volts, then I can say with fair amount of accuracy or with less amount of error, I can neglect that. Okay? So, I am just trying to see what conditions you get that Millman and Halkias formula. So, it is the same formula. After all, it is square law that also is put there. So, I neglect this, I get VGS plus Vp 0 square. Okay? And I substitute for this, I do not substitute. That is where the simplification is, in the sense you do not worry. This is circuit engineer approach totally. You do not worry what is mobility and all the things. You plug this or combine all this together into a term called IDSS. Okay? This is a term which Millman Halkias gives. IDSS. What is that? That is that quantity. Now, so what is that IDSS? IDSS is nothing but G naught V p 0 by 4, okay? And IDS is the saturation current. These are form currents. These are expressions for current in this region. Whatever we are talking of is only in the saturation region, okay, because we have made certain assumptions that VBI minus Vp 0 VGS plus VD sat is equal to Vp 0. That assumption we have made, it is in that region. The same equation here holds good. Okay. So, what we are telling is this current is IDSS into 1 plus VGS by Vp whole square, and if I put in that expression VGS equal to 0, if in that expression I put VGS equal to 0, then I get IDSS. In fact, you have made two things now. You have neglected VBI, made it equal to 0, and now if VGS equal to 0, okay, the current that would flow at saturation is that IDSS current. In fact, it is actually the current which you get and VGS, VBI both are 0, because you have neglected that already. In other words, if you look into this diagram, this is actually 0 here, VBI 0, VGS 0. From there it is moving right up to pinch off here. Okay? That is the situation that you have got, like this. See, from here, if I go on up to this point, right up to this point like this, linearly if I go, what is the channel area? Effectively it is A by 2, A and 0, A by 2 on average. Channel conductance will be G naught by 2. What is the voltage here? Vp 0, okay, it is virtually Vp 0. Vd sat equal to Vp 0 in that case, because Vbi minus Vgs equal to 0, so that is Vp 0. So, Vp 0 divided by the resistance is a current, saturation current. So, IDSS would mean that this is Vp 0 divided by the resistance of that portion, but that would have been G naught by 2, but it is G naught by 4 because it is not linear. This is varying a square of the voltage. So, it is actually coming like this. So, instead of being like this, instead of being linear there, it is bending down that like that, so that the effective area, channel height on an average is A by 4. That is the implication. Okay. So, the Halkias-Millman formula is IDSS into 1 plus VGS by Vp 0 square. It is the same as that what we have got, except you put the VBI is small compared to Vp 0. It is just what we said now. IDSS is the maximum drain current that flows when the gate is shorted to the source, that is VGS equal to 0. I just now explained that. So, IDSS is G naught into Vp 0 by 4, channel conductance is G naught by 4. If it is linear, it is G naught by 2, but it is still less because the curve is down going like that, because the effective channel thickness is A naught by 4. Okay? The effective channel thickness, if it is linear, is instead of saying effective, it would be correct to say it is average. It would have been A by 2, but it is A by 4 average. It is just a physical meaning into what we are talking of. Now, so what we say now is this is actually the current which flows when the channel drop is Vp 0 and channel conductance is G naught by 4. All that we have explained now. Okay. So, finally, where is this formula applicable? This formula is applicable when VBI is very, very small compared to Vp 0, or in devices where Vp 0 is large. You can't do anything about VBI, that is there 0.8 volts or 0.75 volts. You can make VBI small, you make a line shorter by drawing a longer line. So, you can make VBI small by making compared to Vp 0 by making Vp 0 larger. So, this is true for devices which operate in the depletion mode. Understand? Because when VBI is small, let us put that. When When the VBI is small, depletion layer width is VDS small, let us say. Let us not talk of that VDS without applying VDS, apply VGS. Okay. If I do not apply any VGS, just VBI itself is there. If I apply voltage between the drain and the source, you have a current flow. That is, with the input voltage equal to 0, you have current because of VDS, drain to source voltage. So, the device is on without any gate voltage. So, to turn off the device, these are terminology which have been beaten up so many times. To turn off the device, you must increase the gate voltage negatively, so that the depletion layer comes off completely like this. When the depletion layer comes off like this, the channel is closed. It is like closing a valve at the inlet of the fluid flow pipe. There is no output. Okay. So, that is why to turn off the device, you must apply negative voltage. Okay. So, the pinch off voltage is large compared to built in potential. That is, the channel thickness and doping is such that the depletion layer is at pinch off is larger than the depletion layer at VBI. That is the condition for which this formula holds good. Today, we may not be talking of such devices, okay, because these are depletion mode devices. You would like to avoid depletion mode type of devices. Why? Without any gate voltage, there is current flow. If there is current flow without gate voltage, there is power dissipation when the input signal is there, not there. Okay. You want the device to work when the input signal comes, and when the input signal is not there, you want it not to perform. It should not perform when the input signal is absent. When it is present, it should respond. Now, it is responding for the input signal, but it is like hitting the fellow, sit down. Okay. It is performing, making him not perform, making the device not to perform the applied signal. That is what you are doing. It is just so Milman Halke's book gives this formula for JFET. So, formulas are same for JFET and MESFET. Now, let us see. This is the formula that we have derived for in general, mu Cs W by 2L into VGS minus V threshold whole square. Here we have not neglected VBA compared to VP0. That means, it would hold good for a situation where VP0 is larger than VBI. It will hold good for a situation where VP0 is not large. It will even hold good for a situation where VP0 is less than VBI. All that will happen will be V threshold voltage is equal to VBI minus, that is the voltage that you must apply, so that the channel is pinched off. If you do not apply any voltage, only VBI is present. Okay. Now, if VBI is small or 0 or close to, is very small compared to VP0, threshold voltage is negative. That is, you must apply negative voltage, so that depletion layer goes through the thing. So, if VBI is small compared to the pinch off voltage, you must apply negative voltage to the gate, whether JFET or MESFET, both. In a JFET is P plus N junction, you reverse bias. Here it is metal semiconductor contact, you reverse bias. Negative voltage apply, so that device is turned off. Threshold voltage is negative. If VBI is larger, if VBI is equal to VP0, you are not able to believe that. If VBI equal to VP0, right at 0 voltage, it is just stopping conducting. How to make it conduction? Suppose I have a depletion layer which goes all the way like that because of depletion layer. To make it conduct, I must open this channel by decreasing the depletion layer width. How can I decrease the depletion layer width? The voltage across that should be reduced below VBI. How can I do that? By forward biasing the diode. So, we have to forward bias the diode, the Shockley barrier diode, so that the channel is opening. Okay. So, which means I must apply plus voltage to the gate to turn on the device. So, VBI is equal to VP 0, I must apply more than with threshold is 0, I must apply positive voltage. Suppose VBI is larger than VP 0, the threshold is positive. Okay. That is, unless I apply certain threshold plus voltage, see, it may even go beyond that. Unless if VBI is positive means I must apply plus voltage, so that it is just about to open. Okay. Now, what does this equation say? In the saturation region, the drain current is actually increasing as square of VGS mass with threshold square. So, if threshold voltage is positive, that is VBI larger than VP 0, that is a characteristic. That is called enhancement type of device. When you say enhancement type of device, what it implies? The current enhances when you apply the voltage. When you say depletion type of device, the implication is you are depleting the current or reducing the current when you apply voltage. So, here you can see threshold voltage is negative. Okay. That is at 0 bias itself, its current is there. I must keep applying negative voltage to cut down the current, and when I apply a voltage equal to threshold voltage, negative voltage, it is turned off. So, difference is here the threshold voltage is the voltage that you must apply to turn off the device, negative voltage. Here it is the voltage that you must apply to turn on the device. But even here you can say this is the voltage at which device is about to turn on, if you want to call it. So, that is the implication of that. Okay. So, now couple of things on this I want to discuss before we go further. Please understand that discussion that we are talking of is true for JFET and MESFET both, okay, because both of them have the one is Shockley junction, other one is PN junction, both of them do the same job of providing a depletion layer, a barrier. So, that is why it is same thing. Now, what we are telling is how do I make this threshold voltage positive? See, you like this particular device, okay? You like this particular device. Why do you like it? When the input signal is 0, current is 0. That is what you want. Power dissipation is 0 when input signal is 0. So, this is the device that you are looking for. So, how do you make that positive? You want to make it positive. You can play with VP 0. You must reduce the VP 0, so that it becomes less than this. Say for example, if this is 0.9 volts VBI, to make it positive, I must have VP 0 1 volt. No, I am sorry, 0.9, I must have VP 0 less than 0.9. 0.8 volts if I have 0.1 volt. So, how can you do that? Okay. How can you do that? VP 0, I think I will don't need this diagram right now, because we have it right there. Okay. PBI P threshold we want to keep positive. So, VP 0 should be reduced to make V threshold positive. Now, VP 0 is Q N d A squared divided by epsilon 0, that is V p 0. So, if I want to reduce this, how can I do that? The parameters that you can play with, one is doping, other one is A. Okay? Which of them will you play? Will you reduce the doping, reduce the threshold voltage, or will you reduce A to reduce the threshold voltage? I am sorry, reduce the P p 0. Reduction of this or this? This is a very tricky question. If you look back, okay, you may not worry in long channel devices much, but if you look back into the MOSFET theory, you will see there the scaling laws. If you see, what you are doing is you are reducing the thickness of the oxide and increasing the doping to control the threshold voltage. Same thing, to control threshold voltage, you would prefer to reduce A rather than reduce doping. Very good understanding for this is, why should you reduce A rather than reducing doping? You prefer to reduce A. What benefit do you get straight away? Reduce A. What benefit do you get from this equation? All other things remaining same. If I reduce A, in fact, I would prefer reduce A, increase N d to keep the threshold voltage at some value. If I want to keep the threshold voltage constant at plus 0.1 volts, I can do that by increasing doping and reducing A. So, that is kept at 0.1 volt. Okay. I would like to do that because I want to reduce A, that will make this C s more, which actually makes the coupling between the gate and the channel better, and that makes also, even from the formula, I d becomes larger. For a given voltage swing, I d becomes larger, or if you want to see, the transconductance becomes larger. So, to get a better transconductance device, you would prefer to reduce A if you want to reduce P p 0. That is how it is done. We will have a better occasion to look into this little later when we talk of short channel devices. Okay. There again we will think of looking into this A reduction. So, in the MOSFET, the focus is to reduce the thickness of the oxide, and we will end up in trouble by reducing the oxide to angstrom level. Here the focus is reducing the channel thickness. Okay. Please remember, when you reduce the thickness, you must have the reduced thickness uniform everywhere over the entire wafer. Because if A is 0.1 micron, okay, in one device over here, I want the same A to be 0.1 micron here. Otherwise, the performance of the device here, the transconductance, threshold voltage, etc., here will be different from here. So, the uniformity, this is the problem which you are passing on to the technologist, asking the technologist to say, I want A to be same everywhere. In the case of JFET, MESFET, I want the T oxides to be same everywhere in the case of MOSFET. Okay. I want the doping to be same everywhere in the case of both JFET and MESFET and MOSFET. Those are the problems which make the life difficult to the technologist. So, the final heat is taken by the technologist. Okay. Now, these are things which you have just already mentioned, that is, the GM is better in, I have already mentioned this in other reference, GM is better in the case of gallium arsenide FET 10 to 15 times compared to GM of silicon MOSFET, because mu n is better, CS is better, because CS is larger than C oxide, because epsilon r is 12.8 in gallium arsenide, epsilon r in oxide is 4. Okay. We have just told that more than once. Now, let us see whatever we have been talking of, how good is that? Do we have to make any changes? Under what circumstances do we have to make changes? That is what we want to see. the assumption in Shockley's model is velocity is proportional to electric field. V is equal to mu into E. Strictly speaking, that is actually true for low fields. As you go to higher and higher fields, velocity is no longer proportional to the electric field. Okay? After all, you cannot have the velocity going on to infinity. Okay? So, let us see that. If you take silicon for example, electric field, okay, volts per centimeter, E the symbol for electric field, then ID, I am sorry, V, velocity. Okay. How does it go? Goes on linearly, and we have used that it is going to remain right through the electric field, right up to the pinch off point we have said it remaining linear, and then we gave up and said okay, that pinches off, that is the condition. And but actually in silicon it goes up like this, saturate. So, you have got a saturation velocity. Velocity saturation effect is there, which is about 10 to the power of 7 centimeter per second for silicon. In fact, the saturation phenomena is true whether you talk of silicon, whether you talk of gallium arsenide, indium phosphide, gallium nitride, anything. The way it approaches may be slightly different. Okay. You may have this going like this, or it may go through a thing like this. Okay. So, I am just not plotting that at the moment, I am just plotting this for silicon. For gallium arsenide also there will be velocity saturation. Okay. Let me just put for the, this is for silicon. For gallium arsenide, what can you say about the VI character, the velocity versus field characteristics? Mobility is higher, that means the slope will be going up like that. Delta V by delta V is equal to mu into electric. Over here, mu n higher implies the slope is higher. In fact, what happens is, we will discuss this later, it will go like that and come back like this. Whether it goes like that or like this, ultimately it saturates. Okay. So, you will have a velocity saturation effect. This is gallium arsenide. We will take a look at the physical phenomena, why it happens, the overshoot is there, all that we will discuss in a couple of lectures later, because that is very interesting and that plays a major role in gallium arsenide device performance. This velocity overshoot here. Okay. This is the velocity saturation. You must write it slightly bigger. That is velocity saturation. Okay. So, what we are trying to tell is this will be true when the fields are low, and ultimately it will be velocity saturation. Let us take a look at this here. It is like that, like this. That is the depletion layer. Current can be written as Q n into V. That is that. In fact, we have used that equation deriving that. V is equal to mu n into E only in this portion. As the field goes on increasing, that proportionality does not hold good. Okay. What is the status here? At this point, the channel height is large. You will satisfy this condition. You will satisfy this condition in most of the portions. Okay. So, if you recall, Okay, I will remove this now. J is q n into v. This is this velocity that we are talking of. We substituted that. Now, n of course will be equal to, all things are ionized, means it will be q into n d into velocity, doping concentration. This is current density, but in the physical device it is the current that we are talking of. Current is actually equal to I d is J into area, and that we wrote it as J into area is how much. See, ultimately we are really supposed to use J into W into A minus H. Okay. Now, you can see this total current is constant. After all, there should be current continuity through the device. Any cross section you take, the current cannot just become more in one place and less in another place. Okay. Current density could change. So, since the current is constant, in fact, in the last lecture we were discussing some of those things. If the current is constant here, the current density becomes H is this, and this A minus H is this. As you keep on moving from the source towards the drain end, A minus H keeps on falling. A minus H keeps on falling means current density increases if I d is constant. If the current density increases, what is the thing that increases? The velocity, which implies as you move from this end to this end, what happens to the velocity? Increases, and velocity increases means you are moving along this curve. That means you are moving into higher field regions. So, okay, supposing you hit this particular region, velocity saturation region, the velocity can become maximum velocity saturation region. This will keep on widening because the voltage drop keeps on increasing. Now, if the velocity has reached saturation here, that is the point at which current will saturate. Okay. Strictly speaking, what Shockley said was not correct. What he said is that the channel pinches off, current saturates. You could easily get the analytical expression, but what really happens is the current would saturate when the velocity somewhere saturates. And where will the velocity saturate? Velocity saturate at a point corresponding to the where the field is maximum, when you reach that critical field. So, at a point at which you reach that saturation field, you have the velocity saturation. It need not pinch off at that point. Okay. Now, to illustrate that, so I d saturates due to channel pinch off at the drain end. That is what Shockley said. What we are telling now is channel need not pinch off. Okay. The channel need not pinch off for the current to saturate. That is what we are trying to tell. All that is required condition is the velocity should saturate. Now, if you just take a look at this, so that means you cannot use that equation. Now, I will give an example before I go into the details of this, which I will take in next lecture. In the next few minutes, I will just discuss and find out, should we talk about the JFET or MESFET etcetera for this current saturation. Supposing I take a resistor made up of semiconductor, velocity is okay. Supposing I take a resistor like that, N type semiconductor, not a metal, not a carbon resistor or anything, and I put a contact here, I apply a voltage here, you will get a current through that like that. This is voltage, this is current. This is the resistor. There is no depletion layer formation, there is no chance for depletion layer formation. I am not talking of surface states and all that. What will happen to the current? What will be the current versus voltage characteristic of this device? Invariably, all of us will say, without exception, we will say V by I is straight. Ohm's law, resistor Ohm's law, but Ohm's law fails beyond certain point. Okay? There is a limit up to which you can hold Ohm's law, that is, field must be small. In a metal, it will hold very well, because carrier concentration is very high. So, current density is actually equal to Q n into V, okay? And current is equal to, so this current will behave once n is constant, n is decided by doping. In the metal, n is decided by the metal carrying electrons. So, this is constant. This is constant here, fixed cross section, whereas here you have that cross section varying because of voltage drop and because of the junction depletion layer widening. Here it is not changing. What will be the IV characteristics now? It follows the velocity variation. As I keep on increasing the voltage, the electric field here, the electric field there keeps on increasing. When the electric field there keeps on increasing, okay, what happens to velocity? I will just put side by side, I think, yeah, I will put that the electric field versus the velocity, if it is like this, okay, since J is equal to I is equal to Q n V into area, the current will follow what the way the velocity follows. So, you will have the IV characteristics actually of this resistor, which will particularly be true when n is small. You will get a characteristic like this. So, the current saturation phenomena is not the propriety of the FET. The current saturation phenomena can take place when velocity saturates. So, what we are telling is the current is saturated in the case of FET not because of pinch offs, it is because of velocity saturation, but it may so happen that pinch off has taken place when velocity saturation has taken place. Here you can see without any pinch off, current is saturated. Okay. That is ID sat, okay, I sat saturation is equal to Q n into V s into area, where V s is that. So, now where does it land us? It lands us in trouble, in the sense, do we accept Shockley's model and under what circumstances can we do that? So, we will actually have just few things I will point out to you, because I will have to take it up in our next lecture, because in the couple of minutes I just point out to you. We make an assumption. I will just go through this assumption and then we will start the analysis afterwards. In fact, finally, we will see that Shockley is right under certain conditions. That is why they were able to use that model for so many years. So, what we do is, whether you have gallium arsenide or silicon, whatever it is, we make an approximation that the velocity field characteristic is linear, then saturates. In other words, instead of saying it like this, we say it becomes like this. What we do is, assumption is the velocity versus electric field, we make it like this instead of like that, or instead of something like that. Whatever be the shape, we make this assumption. And there are things like this. the equation 1 which pinch off condition you cannot use. So, you make this approximation for the velocity versus field, where velocity is proportional to electric field in this region up to electric field less than E of s, critical field, saturation field, and velocity is equal to V of s, saturation velocity beyond that. That means piecewise linearization. Okay. V is equal to mu n into E, that is the saturation velocity. So, once you hold these two, up to that point it is mu n into E, and from it is saturation, and the velocity saturation is that quantity. To use that, we have to find out both I d and V d such which are both unknowns. How to find that out we will discuss tomorrow. In fact, this is the modern understanding of this particular device. See you in the next lecture with this approximation. Straight get into analysis.